In this video, we discuss the mean value theorem for integrals. It says if f is continuous on the interval from a to b, then there exists a c in the interval from a to b such that the integral from a to b of f of x is equal to f of c times b minus a. And this number f of c is called the average value of f on the interval from a to b. I tend to denote it this way. And it's equal to 1 divided by b minus a times the integral from a to b of f of x dx. I tend to think of f average as sort of the average height of the function. When we evaluate this, we get this area under the curve. If we take that area and then we divide by the length of the interval, we should get an average height. And that average height is this function value. What the mean value theorem says is not only do we calculate f average in this way, but we're guaranteed an x value on the interval from a to b, where f is actually equal to its average value. So basically, it's the height my rectangle would have to be so that the area under that y value, or the area of the rectangle with that height, is equal to this area under the curve. So I know basically what I'm trying to do is I'm trying to draw a horizontal line so that the area above the line and the area, that white area below the line, are the same. So I think if I do that, oh no, that's a little bit too low. I think that one's probably right. I'm going to say that's approximately f average. And does that make sense? If I take the area of this rectangle, and it's supposed to be a horizontal line, it looks like it's sloping a little bit. It looks like it has a tiny positive slope. But if I take the area of this rectangle, it's supposed to be the same as that blue area. Now, on the interval from this x value to this x value, the area of that rectangle is an underestimate of the true area under the curve, because the actual area under the curve is this area plus this extra area. But on the interval from C to B, the area of this rectangle is actually larger than the area under the curve because of that white area there. So you want to choose your y value so that that area and that area match, so that those are equal to each other. So that if you wanted to, you could take this area and just sort of place it in there, and we would see that the area under that horizontal line and between x equals a and x equals b is equal to the area under the curve given by y equals f of x. So this is my y equals f of x function. Okay, and then you said, okay, the mean value theorem for integrals says that if f is continuous, then there has to be a c value on that interval where f is equal to its average value. So we have f average equals f of c, and c is between a and b. And you say, well, I think this is my average value, and the x value that corresponds to that y value is this one. So if I choose to evaluate f at x equals c, that is the y value that we should choose, so that the area of this rectangle equals the area under the curve. So that's what the theorem says. Now we might want to prove it. Now, in order to prove it, we're going to use the intermediate value theorem. Here is a restatement of the intermediate value theorem, just as a review. Now, we learned about the intermediate value theorem in, I think, the first chapter when we discussed continuity. We said, if f is continuous on the interval from a to b, and if f of a is not equal to f of b, and k is a number between f of a and f of b. So we might have f of a is less than k, which is less than b, or we might have f of b is less than k, which is less than f of a, depending on what the graph actually looks like. I'm not sure which one of these y values is higher. If all of those things are true, then f of x equals k has a solution on the interval from a to b. So in other words, there is an x value so that the corresponding y value on the function is equal to that k value. So if we wanted to, we could draw a picture. So let's say this is our a, f of a. And here's b. This is our b and our f of b. And we've assumed our function is continuous. Those two values are not the same. So anything can happen in between this. I mean, it might have lots of hills and valleys in between, or it might just be a line segment. We don't actually know what it looks like, but let's just say it looks like this, okay? If k is any number on between f of a and f of b, so let's say y equals k is this, then f of x equals k has a solution. Say, well, what is the solution? It's that x value. We called that c. Sometimes they say there exists a c such that f of c equals k, but I just like to remind ourselves, we're just saying that this horizontal line, y equals k, has to cross that graph of y equals f of x if that k value is between f of a and f of b. Or in other words, we're saying if our function is continuous and f of a and f of b are not the same thing, then basically our function is guaranteed to have all of these y values, all of the y values between f of a and f of b are guaranteed to be associated with a particular point x in between x equals a and x equals b. And you might be saying, well, I also get some extra y values, right? For this particular curve, the function also takes on y values that are larger than f of b. What about those? Well, this theorem doesn't say anything about those. This theorem just says that we're guaranteed to have every single y value between this y value and this y value because the function is continuous. We could have just drawn a line segment and then we would see exactly how every x or every y value in here would map to a particular x value in here. But I mean, the graph could have looked like this instead. I mean, it could do lots of different things. We might actually have 1, 2, 3 solutions corresponding to the f of x equals k equation. We don't really know. But if the function is continuous, what we're saying is we're guaranteed at least one solution. There's at least one x value on this interval between a and b that maps to this y value, y equals k. That's what we're going to do to show that this f of c exists, but that only works if we've got two separate values for our function f. And actually, if f is constant, we wouldn't have two separate values. So we're going to use intermediate value theorem for most of the proof, but we have to split the proof into two cases. In the first case, we'll just say that f is a constant. Let's say case 1, f is constant. Then we have the integral from a to b of f of x dx. Let's say that constant is k. F is constant, it's obviously continuous. And the theorem says there exists a c and a to b such that the function value times b minus a is equal to the value of the integral. So, well, yeah, actually any c value would work. I could choose this c or this c or this c. Pretty much every single x value in here maps to the same k value. So in that case, the integral from a to b of f of x, if we wanted to, we could evaluate it directly. It's the integral from a to b of k. Using the fundamental theorem, if we wanted to, we could say that that's k times x, where x goes from a to b, whoops. And then you substitute b minus a. So the value of the integral is k times b minus a. Well, that's equal to f of c times b minus a. Not just for one c value, but for every c value in the interval from a to b. So this is actually true. F of c equals k. Well, actually, for every c in the interval from a to b. So actually I have infinitely many c's that map to that y value of k. I hope that makes sense. Okay, so that's case one. If k is constant, or if the function is constant, obviously the average value of the function and the function value itself are the same. And of course, the values of c are just any x value you want between a and b. They're actually infinitely many. Just pick an x value between a and b. There exists at least one, turns out there are infinitely many. Now, in part B, we say, okay, what if f is not a constant? If f isn't a constant, then we're guaranteed that f has an absolute min and an absolute max on a to b by the extreme value theorem. Well, we're guaranteed that f has an absolute min and absolute max by the extreme value theorem, but we weren't guaranteed that those were unique. If f is not a constant, we're guaranteed that they're unique. So f has an absolute min and an absolute max on the interval from a to b, such that the minimum value of f on the interval from a to b is strictly less than the maximum value of f on the interval from a to b. So the point is that they're different values. And we need them to be different in order to use the extreme value or the intermediate value theorem, which requires the function values to be different from each other. Okay, so we have an absolute max and an absolute min. So we know that f is between its absolute max and an absolute min for every x value on the interval. Now, if we integrate these, each of these three functions on the interval from a to b, this is what we get. And I really should include that subinterval under it, but I'm just leaving that off. I think it's implied. Now, the minimum and maximum value of the function on the interval from a to b is just a constant. It's just one particular value. So you can factor that out. So we're going to end up with that constant times b minus a. You can use the fundamental theorem if you want to. So you'd have this constant times x, plug in b, plug in a, and subtract. You can do that. Or you can just think, well, what's the area of that rectangle? If the height is the minimum value of f, and then the length is the length of the interval from a to b, we're going to get the height times the length, or length times width for your rectangle. And you'll have that here. And on the other side, the maximum value is also a constant, so you can factor that out. And then this is the exact area in between, right? If the function happens to be positive or non-negative on the interval, and it's the net area if the function happens to be negative. So if this is my function, let's say we're on the interval from a to b, here's the maximum value of the function on the interval. Here's the minimum value of the function on the interval. The area under the curve is that area. But if we compare that area with the area of this rectangle, the rectangle that starts at x equals a and ends at x equals b, and has a height of f minimum, obviously the area under the curve for f of x is greater than the area of this rectangle. And then you'd say, okay, well, what about the area of the rectangle with f max as its height? So I'm looking at sort of this larger area now. Well, obviously the area of that larger rectangle is greater than the area under the curve. This area is greater than that blue area that I've shaded in. So we're saying the area of this smaller rectangle is less than the blue area, and the area of the larger rectangle is greater than the blue area. So the area under the curve is squeezed in between those two values. And now if you want to, you can divide all three parts by b minus a, and then you'll have that average value in the middle. So we've got the minimum value of f on the interval from a to b is less than or equal to the integral from a to b of f of x dx divided by b minus a, that's the average value of f, and that's less than or equal to the minimum value or I said maximum value of f on the interval from a to b. So we know that the average value has to be between the minimum and the maximum. And that is sort of consistent with our expectations. If I want to find an average value for that function, so that the average value is that area under the curve divided by the length of the interval to get an average height, well, shouldn't that line be somewhere in here so that the area above the line and then that area below the line sort of match each other? I think that makes intuitive sense. But now we say, okay, how can I prove that there is an x value on the interval of interest that actually gives us this as its y value? So how can I find a function, or how can I find a function value on the interval that actually has this as its y value? So I'm looking for f of c to equal this, and I want to be sure that c exists so that f average actually maps to a particular x value on the interval of interest. And I think that we can all see that it's going to. It has to have some value in between from there to there. Well, in order to do that, we're going to use the intermediate value theorem. Now, it looks a little different because we're using f in a different way here than we're using it over here. But this is what it says. It says if the function that we're interested in is continuous and the function values at the endpoints are different from each other. So I've got f of a and f of b, and they're not the same, and k is some value in between, then there is an x value so that f of x equals k has a solution. So there is a c value, if you prefer, such that f of c is equal to k, where that c is in the interval from a to b. Say, okay, well, let's look at this. Whoops. This inequality says that the average value is between the minimum value of f and the maximum value of f. Let's look at our picture again. In this particular picture, f max is associated with a value, I'm just going to call that C1. So the function achieves its maximum value at some x value on the interval, and f min is associated with an x value C2. Since f is, continuous, and we're on a closed interval from a to b, we're guaranteed that there are x values on that interval from a to b where our function has an absolute max and an absolute min. Okay, so this interval C1 to C2 or C2 to C1, depending on which one happens to be less than the other one, is we never really know. I mean, the minimum could have occurred over here rather than here. We could have drawn the graph going this way instead of this way. But this interval from C1 to C2 is contained within the interval from A to B, and our x value, the x value that corresponds to this average value of x on the interval, has to be in between the x value that caused or that maps to this minimum value and the x value that maps to that maximum value by the intermediate value theorem. So we'll say, the following. Let's say, suppose f of C1 is the minimum value of f, and f of C2 is the maximum value of f. Of course, we're talking about on the interval from A to B in both cases. And suppose, let's say that C1 is less than C2. Then the interval from C1 to C2 is contained within that larger interval from A to B. And since our function f is continuous, and f of C1 is not equal to f of C2, there exists a C between C1 and C2 such that f of C is equal to that value in between, the average value of the function. I hope my logic is, I hope there's no problems with my logic there. That's by the intermediate value theorem. And if you're saying to yourself, are you sure that that's legal? I think it is. And I guess, should we say that this is a closed interval? No, I think it's an open interval. Okay. So suppose f at C1 is the minimum and f at C2 is the maximum. Actually, the reverse of what I drew in my picture here. Then I said, and suppose C1 is less than C2, just to make it clear. Then we have the interval from C1 to C2 is included in the interval from A to B. Let me draw a picture that's consistent with that. Here's x equals A. And at C1, we want a minimum. And at C2, we want a maximum. So maybe our graph looks like that. And the integral from A to B of f of x looks like it's sort of tilted, sorry. Is this area. Okay. So we say since f is continuous and f at C1 is not equal to f at C2, and this value is just a y value in between, that's our k from the intermediate value theorem. So k is a number between those two values. Then f of x equals k has a solution between the x value that corresponds to the right endpoint and the x value that corresponds to the left endpoint. So if this is our k, we're saying f of x equals this number has a solution on that interval that starts here and ends here by the intermediate value theorem. And then what would my average value have to be? Does that look right? F of c, is that f average? Is this area of that rectangle approximately equal to the area of that, or that blue area? I think it might be. I think it might be. Okay, so f of c equals that, and if you want, you can multiply both sides by b minus a, and you get this equation. Since f is continuous on the interval from a to b, there exists a c in that interval, so that the integral from a to b of f of x equals f of c times b minus a. So this is the area under the curve. If we divide by the length, we get this y value. It's the average height, and the theorem says that there is actually an x value on the interval from a to b where that function achieves its average height. In this picture, if this line was right, and I think it actually should be a little bit higher, the corresponding c value would be right there. In this picture, I think f average is probably right there-ish. So that area, it matches that area. Maybe it needs to be a little higher. And then here, I think that is my f average. And you'd say, well, where's the x value? Where's that c value that we were promised? Well, it's that one right there. And notice it's between C1 and C2, because the minimum value of f is down here. We see that that area lies entirely inside that blue region. So f min times b minus a, that's the area of that rectangle, is less than this blue area. And f max, it's right here. If we look at the area of that rectangle, it's obviously greater than that blue area. So that blue area is squeezed in between, and we say, well, there has got to be an average height between these two heights, or there has to be a y value, or if we're trying to find an x value that corresponds to this y value, well, there has to be one because our function is continuous. And the minimum value and the maximum value are different from each other. So the intermediate value theorem guarantees that there is an x value such that f of x is equal to this on that interval. And the interval, it starts at the x value that maps to the minimum and ends at the x value that maps to the max. So if C1 is less than C2, it looks like this. And of course, if C2 were less than C1, I would just write this as the interval from C2 to C1, but everything would be exactly the same. I just write C2 and C1 here, I'd write C2 and C1 here, and then I'd write C2 and C1 there. And then we'd have f of c equals that. So, and nothing else would change. I just needed to choose an order so that I could write that interval in a particular way, as opposed to saying that one or the opposite one. Just put the smaller number first. That's the idea. Okay, so that is the proof of the mean value theorem for integrals. There is an x value that maps to the average value of f, and the average value of f just comes from taking the area under the curve and dividing by the length to get an average height. Let's apply that to a particular function now. So it says find the average value of f equals sine of x on the interval from 0 to pi. I always like to start by graphing. Sine of x looks like this. It repeats itself every 2 pi. We're also asked to find all of the x satisfying f of x equals f average on the interval from 0 to pi. Well, I think we can see that the maximum value of the sine of x occurs at x equals pi over 2. The maximum value is 1. And the minimum value of or y equals sine of x, excuse me, on the interval from 0 to pi is obviously 0. That's the smallest y value there. So this will be the integral from 0 to pi of sine of x divided by pi minus 0. So I end up with 1 divided by pi times the antiderivative of sine of x, evaluated at 0 and pi, and then we subtract. So we just compute the antiderivative. You say to yourself, well, what do I take the derivative of to get sine of x? Negative cosine of x will work. Evaluate at 0 and pi and subtract. So we have negative cosine of pi minus cosine of 0. Subtracting a negative is adding. Cosine of 0 is 1. Cosine of pi is negative 1. So this is a negative 1 times a negative 1, which is positive 1 divided by pi. So f average is 1 over pi. You'd say, oh, 1 over pi, what is that? It's approximately 1/3, right? 1 divided by 3.14. The pieces are a little bit larger, right? We're not dividing by 3, we're dividing by pieces that are larger than 3. So it should be a little bit smaller than 1/3, right? Denominator is larger, so the fraction should be smaller. But it's approximately 1/3. F average is right there. Now we're asked to find all x values in the interval from 0 to pi such that f of x equals f average. So I want sine of x, that's my f of x, to equal f average. Goodness, I don't know. X will equal the inverse sine or arc sine, or excuse me, I wrote arc cosine. Arc sine of 1 divided by pi. But there are going to be two values. There's going to be that one. We'll call that, well, actually, I think I'll call that x1. There's another one over there. We call that x2. So we'll have two of them. You might say, how do I know what those are? Well, if I use the arc sine button on my calculator, I'm going to get two values. If I were to draw triangles, I would draw triangles in quadrants 1 and 2. Here's a triangle and here's a triangle. You want to draw right triangles. I want the sine of my x value to be 1 divided by pi. Now sine is opposite over hypotenuse. Remember from trig, we have that mnemonic SOHCAHTOA. So when the side opposite x in my triangle is 1, the hypotenuse is pi. Now, the first value that I will get is arcsine of 1 divided by pi. That's going to be some number between 0 and 90 degrees, or between 0 and pi over 2 radians. But then the second angle has the same reference angle, but it's actually this angle, the angle from here to here. So the second angle, that x1 is the arcsine of 1 divided by pi, and x2 is going to be pi minus the arcsine of 1 divided by pi. And I'll use the calculator to find out what those are. So let's do that on Desmos.com. So we've got the integral from 0 to pi of sine of x. Which was 2. And then the average value of f, oops, is 1 divided by pi minus 0, which is pi, times that integral. Did I make a mistake? Yes, I did. I made an arithmetic mistake. I said cosine of 0 was 1 and cosine of pi was -1. Let's look at my paper again. But then I said I had a 1 there. I don't know why I said a 1. I had 1. Negative, or this is 1 plus 1, which is 2. So this should be a 2, which means that's a 2, which means that's a 2, which means that's a 2, means that should be a 2, and that should be a 2. And that means instead of being here, my average value should be a little bit higher. Should be at 2/3 rather than 1/3. And actually, that actually seems to make more sense to me as well. F average. That's my claim. All right. Question is the area of this rectangle the same as the area under the curve? And I think it might be. If I tried to draw the area of this rectangle, so is that the same as the area under the curve? I don't think so. Okay. So we know that those are our values. Let's go back to Desmos. Okay, so this is the interval or the area that we're interested in. And that area turns out to be 2. I think I want to make my heights different, or my range of values different. Let's go from -2 to 2. It's going to stretch it a lot, but there we go. So that's what we're interested in. Okay, so this is my graph. That's the area under the curve. We found that the area was 2, which is relatively easy to find. So the average value of f is 2 divided by pi, or it's this approximately 0.637. Let's graph that, y equals f average. And then we can say the corresponding x values are x equals 0.69 and x equals, x equals 0.69 is the x coordinate there, and x equals 2.45 is the x coordinate there. You might say, how do you find that? Well, we'll just let x1 be the first solution, and that's the arc sine of, we said 2 divided by pi. And let's plot x1 and f of x1. Yep, it is that value. That's what I was expecting. That's what I was hoping. So we get that arc sine of 2 divided by pi. And then remember from our pictures, I'll show you my paper again. It's a little bit hard to see. Remember those triangles? We had one solution in quadrant 1 and one solution in quadrant 2. They have the same reference angle. So the reference angle for this one was the arc sine of 2 divided by pi. This one has arc sine of 2 divided by pi as its reference angle, but we have to subtract that reference angle from pi. So x2, no, you can't really see it very well. I guess the whole point was to focus on just the big picture. Kind of ironic because I showed you a tiny, tiny picture instead. Let's see. I don't know if that's the right use of that word ironic. I'm a math person. I've never, ever since that song came out, like I don't know what ironic means anymore. So x2 is pi minus that reference angle. And let's plot x2, f of x2. And yeah, those are the points of intersection. So those are our two solutions. What did the question say? It said, find the average value of f on the interval from 0 to pi. It turned out to be approximately this 0.637, which is 2 divided by pi. And then we were also asked to find the x values. How did it say it? Find x values in 0 to pi, such that f average, or f of x equals f average. And the x values were these two. So that's a simple application. There are also some really neat applications involving like average force and average values of various functions from physics and biology in the textbook. in the section where this material is covered. I don't remember the section number, but it's the section on the fundamental theorem of calculus. It includes the mean value theorem for integrals, average value, the net change theorem, and both parts of the fundamental theorem. If you do your homework, or if you read just the problems in the end of this section, you can see lots of interesting applications. Computationally, though, it's very easy. You just find the area under the curve using the fundamental theorem, divide by b minus a, and then to find the corresponding x values, or the x values that correspond to that y value equal to f average. You just set f of x equal to f average, and you solve for x the way you traditionally would. And if you've got some trig functions like we do, you want to think about, all those triangles in the xy plane and how many solutions you should have. Because if you just use the arc sign button on your calculator, you'll have one solution, but you'll accidentally forget the second one. So we want to make sure that we understand what's being asked of us, make sure that we find all the possible solutions. And if you're unsure of that, it's helpful to graph it first. If you graph it, you can tell I'm supposed to have two solutions. So that's how I knew. I'm going to have to draw triangles in quadrants 1 and 2 in order to find both values.